Okay, so this is work I've been doing as part of my PhD in Brazil with the help of these great people. I'll be trying to describe why we're interested in chaotic variability, what's it in the real water. Hopefully you'll find it interesting. But first I want to give some context. Where does this fit in the general context of climate science? So for me, there's a few ways to look at this, or rather a few points to make. So if you're familiar with CMIP, you'll know that in the latest round of recommendations, the ocean resolution can be as high as a quarter degree, and perhaps in future iterations even higher resolution. That means we can see large-scale turbulence in the ocean. That's a sign that there is chaotic variability that's present. That's mesoscale eddies. So it's good to look at that, at the variability that this can introduce for climate as well. Something that's more specific to the ocean, some idealized model studies have shown that atmospheric forcing of any periodicity will excite some intrinsic modes of interannual variability in the ocean. What this means is, regardless of what happens in the atmosphere, if it's just stochastically varying, if you have a climatological cycle, etc., there are some modes of variability that are specific to the ocean, and they will be excited by any atmospheric forcing. That's in an uncoupled model. So first sort of conclusion, higher resolution in the ocean will mean there is some chaotic and intrinsic oceanic variability. We'd like to investigate that and how it can impact oceanic features. This is something that's the Occiput project, which I'm part of, has started doing already. Just to give a very brief overview, the impact of chaotic and intrinsic variability has been found to be significant for things like sea level anomaly, the Atlantic Margin or oceanic circulation, the position of the Croatia extension, the ocean deep content. If you're an oceanographer, all of these mean you'll understand that chaotic variability is significant and important for the ocean. Okay, so this is what I'm doing more specifically. This is the data I'm using. I'll start with what's on the left. I have two data sets. What I'm doing, one of them is a model, ocean model based on NEMO. It's an ensemble, specifically, it's got 50 members in the ocean, but that are generated using stochastic perturbations. I'll come back to that on the next slide. They all see the same atmosphere, they have the same atmospheric forcing, so it's a forced ocean model again, and the differences that we will see between the members are oceanic in that sense. I'm also using an observation-based data set called ARMO3D, so it's gridded observations, there's no physical model. Just take observations from Argo flows and satellite altimetry and put them on the grid. That's the sort of reference. Here on the right, what I'm showing is sea surface height. It's a snapshot from one of the members of the model. What I want to insist on, so this is a quarter degree model, and you can see all around here there's lots of turbulence. We can see the turbulence, it will have an impact on what's going on in the ocean. And specifically this box is the area I'm focusing on. It's where we find the 18 degree water. And along the Gulf Stream, there's lots of eddies, so great, I'll have lots of chaos to look at. Yeah, this is what I was saying. This is where you find the 18 degree water. Before I talk about the 18 degree water in detail, I want to take some time to explain how this ensemble was built and how we're analyzing it. So it's an ocean model, started with a 20-year spin-up, and the stochastic perturbations that I've mentioned, so they were turned on for 1 year in 1993. 50 sets of perturbations generating 50 slightly different oceans. The stochastic perturbation is designed to represent the subgrid uncertainty. So for 1 year you perturb your ocean for 50 different oceans, you turn the perturbations off after a year and integrate for 19 more years. This way, sorry, I should have mentioned, the x-axis here is time and y can be any variable that you're interested in. So this way you've got 50 different oceans, they all see the same atmosphere, they have some uncertainty linked to chaotic variability because it's fundamentally the initial conditions that you're changing. If you stop at any one time step, you can draw a PDF of that y variable that you're looking at, and you can define a few things that I'll be using. The ensemble mean, we call this the forced variability. That's because it's what all the members have in common. And then the ensemble dispersion at any one time step is an image of the intrinsic variability. It's the diversity between the members. A very important point here is, I mentioned what they have in common, the ensemble mean, we call this what they have in common in the forced variability. We can say that because the air sea fluxes are identical for all the members. So not just the atmosphere, but the fluxes as well. For each time step, you can compute air sea fluxes for all of the members, and instead of using that to integrate to the next time step, we take the ensemble average, or the ensemble average is taken and is used as the forcing. So they really all, the atmosphere does the same thing to all of the members. That's why we're saying what they have in common is the atmospheric forcing. Right, there's a lot going on here. Just trying to define the 18-degree water that I've talked about. There's no need to focus on all the details, I just put them in if anyone's interested and wants to discuss. The main point is, okay, first, it's a mud water. What's a mud water? That's a pool of very weakly stratified water. It's formed by air sea fluxes. Because it's weakly stratified, we're using Ertl's potential vorticity to define it. Basically, it's a function of the vertical gradient of density. So low PV will mean, low potential vorticity will mean very weakly stratified. That's one thing we'll be using to define the mud water. The three criteria you talked about using are the geographic box, in a certain density range, and a maximum stratification, maximum potential vorticity. I'll describe this on the plots here. So the top row is a horizontal section at 230 meters depth. The white blob here is the North American coast. You can see here's Cuba, here's Florida, Cape Hatteras, and then Canada. I hope that helps you locate things. So whatever is in color, the colors are potential vorticity. Whatever is in color is the geographic box that I mentioned. You'll notice this dashed line here. I've got a meridional section at the bottom row. The other thing I want to talk about here is if you look at the bottom row, okay, left column is March 6th, just the end of winter in one of the members of my ensemble. This is a model, by the way. So end of winter, you've got a very deep mixed layer. This black line here is the PV, maximum PV value that I've mentioned earlier. So anything that's lightly colored outside of this line is very weakly stratified. What we see here is a deep mixed layer, goes down to around 400 meters in this meridional section. And in November of that same year, you can see a pool of weakly stratified water. That's the remnants of the previous year's mixed layer. I don't know if that's clear enough. There's a thick, very dark colored here that's seasonal stratification. That's the thermocline that's formed above this pool of weakly stratified water, above this mixed layer. This is the 18-degree water. It forms in the winter mixed layer, isolated from the atmosphere over summer, and you can define it as a closed volume, and you can do all sorts of statistics on it. So that's how I define it. So in red here is kind of the scientific question driving this work. It's something that's defined, there's strong seasonal cycle. We know there's chaotic variability in this region. How important is this chaotic variability for the 18-degree water? But before we can answer that, I'm trying to be a physicist, so I have to make sure what I'm talking about in the model world makes sense in the real world. So this is a brief comparison to what I mentioned, ARMA 3D, the observation-based product. Basically using the same sorts of criteria, I can define, so right column is the observation-based product, and left column is the model. Top layer is a winter average over the whole period, and bottom layer is a summer average. Main point here for me at least is that you can see the same process. Mixed layer deepening in winter, the model on the left, and the observations of normal 3D, I should say, on the right, getting isolated over summer, and you can define a blob of weakly stratified water with some interesting characteristics. The particulars, the quantitative values of potential vorticity and density are different due to model biases. However, the physical object is the same. It has the same dynamics and it has comparable properties. So we can say things in the model and expect that they make sense in the real world as well. So well, hopefully I've convinced you of that. So if I want to say things in the model world, I want to exploit the ensemble aspect of it. So I put this box here as a reminder of the ensemble mean and the ensemble spread. The main point I want to talk about with this slide is I can define an intrinsic variability, that's the time average of the ensemble spread of the ensemble variance here. So this is the intrinsic variability in the ensemble. The forced variability is the time variance of our ensemble mean. Like I mentioned, it's forced because it's what's common to all members. We consider that this is the effect of atmospheric variability. And then total variability can be defined when it's the ensemble average of the variances, time variances of all members. And we have this very useful property. The total variability is the sum of the forced and intrinsic variability. And that means it's very easy to quantify the importance of intrinsic variability, just get the ratio, intrinsic over total. And that's exactly what I did. So, I've defined a closed volume for 18-degree water, and that means I can compute things on that. Like, this is the volume, interannual volume anomaly in that blob, in that closed volume, and this is the average temperature, interannual temperature anomaly over that same volume. Each of the gray lines is one of the 50 members that I've mentioned. The thick black line is the ensemble average, so you can see they follow a common behavior, but they diverge around it. So there's, anyway, sorry. There is a sort of common behavior that's perturbed by the chaotic variability. That's what I'm trying to say. And depending on the variable that you look at in the 18-degree water, you can see that the chaotic variability is 10 to 44% of the total interannual variability. So even for mode water, for something that's controlled or formed with a very strong seasonal cycle, we simply cannot neglect the chaotic variability, the impact of chaotic variability. This is a different way of looking at it. I don't know if people are familiar with Taylor diagrams. I'll explain this quickly. The way you do this, you get a number of time series, you use one of them as a reference, and you correlate the others to that reference. Not only correlate to it, you compare the others, the variance of the others to that reference. So I've used a time series from the Arnold 3D observation-based product as a reference, and I've compared each of the 50 members of my ensemble to it. So each of the blue dots is one ensemble member and compared to the reference. The angle to the vertical is the correlation, distance to the origin is the ratio of the standard deviation of the time series you're testing over the reference. And those gray lines you see here are the root mean square error. So 0 when you're at the reference point, 1 correlation of 1, and ratio standard deviations of 1. So this is another way of looking at the impact of chaotic variability. You can see that the ensemble average here has an okay correlation to the reference time series, to the observations. It's slightly less variable. So the forcing does okay things, but if you look at the chaotic variability, what it adds, sorry, I should mention this is the volume, looking at the volume time series. As soon as you include the chaotic variability, so you're adding something on top of the ensemble average, your correlation can vary from as low as 0.4 to as high as 0.75. And the ratio of the standard deviations is also quite variable. So chaotic variability will add lots of things on top of the forced variability. And if you only have a single model run, you don't know which of these blue dots you're on. You can't really say, there's an uncertainty that's linked to that chaotic variability. And so far as I'm aware, you can't estimate it without an ensemble. So this is what this is contributing. Something else I wanted to point out, if you take the average of all the blue dots, you've got a slightly lower correlation than if you take the ensemble average. We interpret this as meaning that the chaotic variability on average decorrelates. On average, it acts as noise compared to reference observation time series. Okay, that was a lot. I hope it was understandable enough. And this is a slide I've added to this talk from some conversations I've had with people in the room. This is the evolution of the intrinsic variability over time. Again, in volume and temperature. This is interannual frequency level, low frequency. So yeah, you can see that there's some time, it takes some time for the spread to develop, the ensemble spread to develop. But once it has, it doesn't grow exponentially. The noise you add is not noise, it's uncertainty. So you're varying around a certain mean value. And that's the effect of the chaotic variability, just adding on to, adding an uncertainty over the sim. Sorry. Just after lunch, a bit difficult. So anyway, you've got a varying chaotic uncertainty that's added on top of your atmospheric forcing. And you can also use this to identify some extreme events and what happened, for instance, what happened in the year 2000, why do we have a much higher chaotic variability or ensemble dispersion in volume and temperature? Something I haven't yet figured out, but one of the interesting avenues of research. And yeah, some people in the lab have looked at keeping the stochastic perturbations turned on for the whole duration of the run, and they say they have a similar result. It doesn't blow up. It keeps varying around the mean value. And yeah, that's it. This is the biggest point I wanted to insist on. The uncertainty that's caused by chaotic variability is rarely quantified in motion models, but it is significant. You can't neglect it. If you have just a single model run, you don't know where you are on that Taylor diagram that I showed. Are you having a poor correlation, a poor ratio standard deviation, or are you being lucky and just having a great model of chance? This is something that needs to be, I think, better quantified and better studied. And yeah, you can use that study, extend that study to all sorts of other features of the ocean. Some people have shown that in the North Atlantic, jet current accretion is linked to the equivalent mode water. Maybe we can find something similar in the Atlantic. Didn't go into too much detail, but there seems to be a periodicity to this intrinsic variability. If any statistics people know how to look into that, I'm very interested. It's been sort of a sticking point. And there's probably some teleconnections with other things in the ocean. Chaotic variability is not located, it's something that's everywhere in the ocean in the model, so it's probably some teleconnections to be explored. Right, thank you for listening. I hope that was interesting.
Some questions?
Two questions. One is, what was the temperature time series that you showed? Is that, although the last one?
Which one?
Yeah, is that average?
So that's the spread of the ensemble spread varying over time. The ratio of the ensemble spread over the total variability. And this is for the low frequency time series. So it's filtered and I've removed the seasonal cycle, removed the mean, or the trend. Is that?
Okay, cool. And the Taylor diagram just, so that's, the green is the average of all the volumes? No.
No, red is the average of all the points.
And the green is the average of all the 18-degree volumes?
Yeah, so this is, the green is this thick black line. It's the ensemble average.
Okay, yeah. And blue is in the red is the average of the blue loss. Okay, cool.
Yeah.
Any other questions? Okay, our science speaker again.